For a decade, AI progress was measured by how we trained models. But as we move into the age of inference, the focus is on proactive agents that can navigate multiple applications and orchestrate complex tasks in real time. To maintain these workflows, a model has to hold on to every detail of the interaction, from the specific data in a spreadsheet to the subtle instructions in a long email chain, all within its active memory. As these tasks grow more complex, the hardware is reaching a limit. In this environment, the primary constraint is no longer how fast a processor can crunch numbers. Instead, the ability to store and access massive amounts of context has become the gatekeeper for the next generation of AI development. This active storage is the key value cache. It's the AI's working memory for past context, avoiding the need to reprocess previous words. When analyzing a massive document, this cache grows linearly until it overwhelms physical memory, causing the system to stall. Solving this by simply adding more traditional GPUs introduces a massive financial burden, the NVIDIA tax, where the cost of the hardware begins to outweigh the value of the AI's output. Google realized that overcoming this bottleneck required more than just more chips. It required a total redesign of the architecture, coordinating the hardware and the underlying math to handle data more efficiently. Defeating the KV cache crisis requires a dual solution: building a macroscopic data center engine designed for massive flow and a microscopic mathematical formula to shrink the data itself. On the hardware side, Google built Ironwood. Unlike a general-purpose GPU, Ironwood is a scalpel. It discards features like graphics rendering to dedicate over 90% of its surface area to the specific matrix math used by AI. This starts with a dual chiplet design that scales up into 64-chip liquid-cooled racks, allowing the hardware to maintain peak performance without overheating. These racks are grouped into superpods of 9,216 chips. Through a high-speed interconnect network, the entire facility functions as one cohesive superbrain capable of running the world's largest models. To manage this scale, Google uses optical circuit switching. This technology uses light to route data and instantly bypasses failures, ensuring that even if a chip goes offline, the rest of the superpod stays in sync. A single Ironwood superpod provides 42.5 exaflops of compute and 1.77 petabytes of shared memory, linked by a data highway moving nearly 10 terabits every second. But hardware capacity is only half the battle. Even a petabyte of memory will eventually be exhausted by the compounding weight of the KV cache. To fix the problem at its source, Google Research developed TurboQuant, an algorithm designed to compress the vectors inside that memory cache. This scatterplot represents the raw KV cache data. It's jagged and erratic, making it difficult to compress. The first stage, PolarQuant, applies a random mathematical rotation to this data. This geometric trick forces those erratic points into a smooth, predictable bell curve. Because the data is now uniform, the system can aggressively compress it from the standard 16-bit format down to just 3 bits per value. This reduces the memory footprint by 6 times. However, this level of compression would usually introduce errors that would make the AI's responses nonsensical. This is where the second stage, an algorithm called QJL, comes in to correct the residual bias. By using just a single bit of information to act as a mathematical error checker, QJL aligns the compressed data with the original high-precision wave. The result is a 6 times reduction in memory use and up to an 8 times speedup in processing, all while maintaining perfect accuracy on long context benchmarks. This mathematical correction effectively removes the memory ceiling for inference, allowing developers to scale long context models without a matching jump in infrastructure costs. The impact was immediate. Independent developers quickly realized that because this math was data oblivious, they could port it to run on almost any existing transformer model. Suddenly, million-token context windows that previously required a server rack can be handled by a standard laptop, bringing frontier-scale capabilities to local hardware. While solo developers are running it locally, enterprises are scaling it globally. Anthropic has already announced plans to use 1 million Ironwood TPUs to power their next frontier models. By combining the brute force of Ironwood with the efficiency of TurboQuant, the memory constraints that previously limited the size of AI workloads have been significantly lowered for the entire industry. Economists call this the Jevons paradox. As we make a resource more efficient, we don't use less of it. We find ways to use it exponentially more. With memory costs plummeting, organizations are reinvesting those savings into longer context windows and more simultaneous users, pushing their current hardware to its absolute limit. These efficiency gains mean an AI agent can now hold the specific, long-term context of a full-time role. This enables new organizational structures where human employees are paired with autonomous counterparts capable of managing multi-step workflows over months of data. Agents can now reason through massive documents and maintain project context for weeks without hitting the memory limits that previously caused them to fail. By integrating specialized silicon with extreme mathematical compression, Google has established a new standard for the cost and scale of high-reasoning AI.